Welcome to the 2020 Earth Science Week webinar series, Earth Material Frontiers. This series is being hosted by the American Geosciences Institute, the Mineralogical Society of America, and the International Raw Materials Observatory. We would also like to thank the sponsors of this webinar series, the International Union of Geological Sciences, Resourcing Future Generations, and the Irish Center for Research in Applied Geosciences. It is my pleasure to introduce Angel Aboud Madrid of the Center for Space Resources at the Colorado School of Mines. He will be speaking to us today about resources beyond Earth, enabling future exploration and the new space economy.
Well, hello everyone, and welcome to Earth Science Week that this year in particular, in 2020, focuses on a very unique topic, and that is Earth materials in our lives. But what I'm going to try to do in this lecture is to push your ideas, your imagination, so you can start thinking outside the box. In fact, outside our sphere, our planet Earth, and look at how space materials will also become quite important in our lives. And how space resources in general will allow us to not only expand our exploration efforts, but also will allow to usher us into the new space economy. But let's start on a place that is familiar to all of you, and that is our planet Earth, in which natural resources have been the driving force behind exploration and also the means to do so. And where natural resources have become now a part of our lives, our economy, and our society. But before we start heading to space into the future, let's look at how resources on our planet can actually teach us on what is that we expect to do in space. So let's actually go back in time, in history, way back to about 120,000 BC, and start seeing how resources have become important since we started roaming our planet. Back then, our ancestors, the Homo sapiens, left their birthplace, their cradle, in the southern part of the African continent. As they started heading to other places because of drought, of environmental degradation, and also of population growth. And so they started heading to other parts of the continent, to Europe, to Asia, looking for basic survival, elements like water and food. And then in the process, they developed technologies that allow them to control fire, to preserve food, and also to create tools to allow them to live in ever more harsher environments. 15,000 years ago, when we crossed to the Americas, it was the time for the first economic revolution, and that was agriculture, that now allowed humans to preserve the food, to store them, store energy sources, and that gave them an opportunity to settle, first in villages, then cities, and then eventually civilizations. Then, about 4,000 years ago, mining and metallurgy started that allow humans to start using resources, not just for survival, but for jewelry and creating religious objects and the first coins and currency. Then, in the 15th century, was about utilizing resources for trade, gold, silver, spices, silk. All of this allow humans now to cross continents and start utilizing resources in a much larger way. In the 19th century, it was about searching for oil all over the planet, oil that still is the main source of energy. But this has not stopped. In the last 20 to 30 years, it has been about looking at those rare elements on the periodic tables, the rare earth, that are now part of your cell phones, the cars that you drive every day, and they're now fueling the renewable energy industry. So as you can see, resources have allowed us to explore every corner of our planet, to live off the land in ever more extreme environments, and they have become the engine of our technological society. So what happened when we started exploring space? And why did we do that? Well, one can say that it was another tale of survival, but this time was between the two superpowers of the day, the Soviet Union and the United States, that were trying to gain the higher ground and also show their technological prowess. When the race was over in 1969, exploration continued. We started sending probes to every planet of our solar system and even beyond. But something happened on our way to heaven. Like in any human activity, We went from curiosity and scientific inquiry to realize that space could be useful to us. And in fact, we're already quite dependent on the space around us. It started in 1962 with the launch of Telstar, the first privately sponsored telecommunications satellite that connected Europe and the United States with real-time communications. And so Telstar started utilizing the very first resource in space. And that is simply the view from above. That has given us weather forecasting, global communications, and the ability to pinpoint every location of the Earth with extreme accuracy by using global positioning systems, and also allow us to start monitoring the health of our planet from up above. Also, this is not only the first resource, but the only commercial activity in space. Telecommunication satellites are a $380 billion a year industry, and it is predicted to grow into the trillions in 30 years. But in order to do that, we're going to have to utilize other resources besides the view from above. And we know that there are plenty of them out there. It's just that we're going to have to start thinking about what exactly we are talking about when we say resources. So it's important right now to define some terms with accuracy. One, a resource has value by its utilization. If not, it's just an element of curiosity or scientific interest. And you need three elements to extract resources from Earth, Mars, or anywhere in the solar system or beyond. And these are the following. You need to have a recoverable resource. That means you know your element with enough geological, scientific, engineering, legal, environmental certainty that you know that you can go after it. That's what's known in the mining industry or the oil and gas industry as a proven reserve. Second, you have to have the technology to recover it. And third, as important, if not more important, is you have to have a customer. There has to be a demand. If not, none of these resources matter. So what I'm going to do in this lecture is go through these 3 points clearly so that you can see how we're going to approach the area of space resources. So let's start by identifying what resources are out there that could be recoverable or of importance. So besides the view from above that we already utilize, and the moment you cross the atmosphere of Earth, you encounter things like ultra-high vacuum or low gravity that can allow you to make products under conditions that are very difficult to replicate on Earth. So they can allow you to make products that you can utilize on Earth or actually in space. In fact, there's some companies already that are developing advanced fiber optics in lower gravity. Then you have solar energy that is unlimited and that can be used not only to power spacecraft, but think about collecting sunlight in orbit and then beaming it down to Earth in microwaves of lasers to specific points so we can have plentiful energy 24/7 without worrying about clouds or trying to cover the whole Earth with solar panels. You can actually utilize this energy and just beam it down to Earth. These are the so-called intangible resources. This is not something that you mine or extract. This is something that you can start utilizing, and in fact, they're going to become quite important in the near term. If we want more concrete materials, more concrete elements, then we're going to have to start our travel through space. So let's go to our nearest celestial neighbor, our moon. Our moon that when we landed there 51 years ago, there was not much hope that there could be anything of use. In fact, if you look at the recordings and the voice from the second man on the moon when he stepped out of the lunar lander, he looked around and said, "This is magnificent desolation." There was nothing there that could be of use to human. There was no air to breathe, no water to drink, no plants, no wood, no cows, nothing that could be used for humans. But our view of the moon has changed radically since then as a result of sending satellites that gave us remote sensing, and also from the rocks that were brought from Apollo, about almost 400 kilograms, and the few grams that were brought in robotic missions from the Soviet Union. And those have transformed the view from the moon from a magnificent desolation to a place that is full of elements that can be of use for a lot of applications. So let's start seeing what is useful on our nearest celestial neighbor. First of all, let's take a look at the two sides of the moon. The near side, the one that we see almost every night, and then the far side, one that we never see. Not because it is dark, it receives 2 weeks of sunlight and 2 weeks of darkness, just like the near side, But because the moon is tidally locked to Earth, its period of rotation is the same one as the one that's going around the Earth. So you always see the same side. Now, what elements are common to both of them that are of use? Well, even though there's no atmosphere, there's a vacuum in the moon, there's plenty of oxygen. About 45% of the moon is oxygen that is tied to the rocks. They're oxidized. Also, silicon, that is so important for the semiconductor industry, there's about 21%. And here where the similarities end. For other elements, you have to now start looking at a little bit about the geology of the moon. And we're not going to go deep on that. Just one geological feature that stands out just by looking at the near and the far side is how some areas are a little bit darker than others. Those dark spots are the maria. This is volcanic material, basaltic. This is lava that erupted and fill out all the impact basins and the craters. And that's why you see this very smooth terrain. The other one, the Terra, that occupies almost 83% of the surface of the moon, is the primordial crust of the moon, an orthothetic material that it has been there for billions of years. Now, fortunately, nature has given us the view of the important elements in the near side, the one that we see from our planet. For example, iron, that is so important for our civilization. As you can see, it's mostly concentrated on the near side, up to 14%, and also a little bit on the far side. Titanium, that is so important for the aerospace industry, again, concentrated on the mare, on the near side. Now, the moon has also this creepy side to it, and that is creep, but with a K. It means potassium, rare earths, and phosphorus. And these are concentrated on an area of the moon that stay liquid when the rest of it was crystallizing. And so they concentrated on this region that is also full of radioactive elements like uranium and thorium. In fact, this is a map of thorium on the lunar surface. Now, contrary to the Earth, in which once we identify the elements, now we have to start probably using dynamite and breaking it up into very thin material so we can process it. Nature has also given us quite an advantage on this, because for billions of years, the moon has been bombarded by asteroids, later on by meteorites, nowadays by micrometeorites. And what these elements have done, they have impacted the bedrock of the moon. And in the process of doing that, they have completely pulverized the material into a very fine dust, about 60 to 70 micrometers in diameter, that fills the entire surface of the moon. This is the material that we call, a more specialized term, the lunar regolith. It's on the very top surface of the moon, and that's why you see the footprints of the astronauts, and you don't see them working on rock, because this material has been pulverized and is very fine in the first few centimeters, and then after that it becomes extremely dense. Now, this is not like dust that you find on rivers or sandy beaches, that they are usually very nice rounded pebbles because of all the erosion of water and wind. Because the moon doesn't have an atmosphere, it doesn't have water going around, it's very different. These are jagged edge particles, agglutinates, glassy material, and they're extremely abrasive, something that's going to have to be considered if you start designing equipment to deal with this very rough material. Now, the moon has also been bombarded for billions of years by particles coming from the sun. The sun has injected this material on the moon because it doesn't have a magnetic field, so it goes directly into the lunar regolith. And so these particles are implanted on the soil. And you have things as important as hydrogen, as helium, as nitrogen, and carbon. In fact, you have other elements that are very rare on Earth, orders of magnitude much in larger amounts, like helium-3. This is an isotope of helium, the one that has been suggested to be used as fuel for fusion energy. Right now we have fission energy on Earth, but if we ever control fusion, think about fusing these two elements of helium and then producing energy directly into protons, directly into electricity without having to heat up steam and go through the steam cycle. Not only that, the residue of this fusion reaction is just helium, the one that you use to fill balloons for parties. So it's a very clean form of energy if we ever get to control fusion and get to use helium-3 as a element. Now, the other element that we search everywhere we go as human is water. So how about water on the moon? When we landed there, there was not much hope that we were going to find any of this, because the moon has these very unique properties. It's aligned only 1.5 degrees with respect to the sun. And so during the typical lunar cycle, every as part of the moon is completely and fully illuminated by the sun. So any hope to find any water on the surface literally evaporates very quickly. But this 1.5 degrees, what it does is that the rays around the moon on the poles are very oblique. So scientists started saying, well, what about if there are certain regions on the moon, on the poles, where the sun rays are very oblique, that have very deep craters that have never seen the light of the sun. And so what about if comets with ice has deposited there for billions of years and also hydrated minerals from asteroids? And what if there could be, on these very cold regions, some ice stored? And so several missions were sent through the years looking with various instruments at the possibility of water and hydrogen. And what they discovered was not only that water ice was indeed there, but other important elements, just like location. You know, real estate is a very important resource here on Earth. Same thing on the moon. And so what they found is that indeed in the poles, there exist these permanently shadowed regions that contain water ice, but as important as those regions that have plenty of sunlight. You know, they're usually called peaks of eternal light. I mean, light is not eternal, but more than 93% of this region is illuminated. So you have power, you have communications, you have light, so you can put a base in there. In fact, the missions that are being planned for the middle of this decade are to be landing on these regions where you can have access to this. Because once you have access to this energy, you can even reflect it down to the bottom of the craters, and you can use this energy to extract the water ice, as we will see later on. What this mission gave us also is an indication of where to start looking for water and identify those regions here in blue where you find most of the water from these missions. And one of those craters was the crater Cabeus. And there was a mission sent in 2009 to explore this very unique crater. And this mission consisted of 2 spacecraft that separated. The white one went in, right inside the crater Cabeus, impacted it, and a plume came out that was detected by the second spacecraft for a few more minutes before it crashed, and also by some telescope from Earth. And on this plume, indeed, water was found for the first time by touching the surface, around anywhere from 3 to 8%. And not only water, all sorts of elements that can be considered contaminants if you want to extract the water, but when you're there in the surface of the moon, you have to be quite resourceful. So any of those could be used for other activities. You got carbon dioxide and carbon monoxide and methane, in which you can extract the carbon, or you have ammonia when you can extract the very precious nitrogen. So these things can also be resources in the future. So what we have learned from these missions is that in the poles of the moon, here you can see the South Pole, there is indeed water ice locked and trapped on these permanently shadowed regions. A very small amount. It's about 3% of the mass that is found on one of the poles. But this is water ice that can be very useful for all sorts of activities, to propellants and human consumables and everything else that we use water for here on Earth. Now you're going to ask, how much water is that? The estimates right now, with the very little information that we have, is that it can vary anywhere from 100 million to 1 billion metric tons of water per pole. Now, how much is that? Well, let's put it in perspective of water on our planet. In fact, in the United States, you can see here regions with a lot of water, like the Great Lakes. Well, the amount of water per pole is equivalent to the water that is found on a small lake in the Great Lakes regions, which is the Lake St. Clair, a very small lake that communicates Lake Huron and Lake Erie. And in this small lake, you know, even though it's so small, you can find plenty of water on the moon. You know, obviously there's not as much water as on Earth, but this little amount of water could last for hundreds of years for a variety of applications, especially in a small scale, as we're going to start doing it at the beginning. So just like on Earth with water and oil, this is a non-renewable resource, but if we utilize it responsibly and we utilize it well, it can help us with a lot of activities that we're going to see later on. So these are the elements that one finds on the moon, but let's keep going. Let's catch up with those amorphous rocks that are all over the solar system. These are the so-called asteroids that vary between about a meter to about 1,000 kilometers on the planet, the dwarf planet series. But most of them are these irregularly shaped rocks that are floating around. And these are not exactly the rocks that we learn, you know, in high school, that they are very nicely defined on this belt between Mars and Jupiter. Actually, these rocks tend to impact each other, and what happens, they end up all over the solar system. And some of them are actually trapped on orbits like the Earth around the sun. Here you can see Earth in this blue orbit, and many of these dots are the asteroids that are very close to that orbit. And these are the called near-Earth objects, and they're of importance because you can travel to those very quickly without having to go to the asteroid belt. And what is that we know about their resources? Well, we know it from their spectrum. That means from observatories on the ground, we can see the type of asteroids and we can classify it in terms of their resources. And there are three important types. The carbonaceous types, or C-type, like Mathilde that we visited in the 1990s, not only has carbon, but these asteroids have about 20% water. Then the S-type, the silicaceous or stony objects, you start seeing metals like nickel and iron, and also non-metals like silicon. And then those metallic types, the M types, in which you start seeing now the noble gases, gold, the platinum, iridium, all of those very precious elements that we find here on Earth. Now, we know about these asteroids not just from spectroscopic observations, but because parts of this have fallen into, literally in our hands. Thousands of these have fallen into Earth as meteorites. And so they're classified in similar ways, and we know the elements of these meteorites so that we can infer from them what type of materials we're going to find once we go to these asteroids. So besides the moon, we can add all these different asteroids, the type C, the S, and the M. And we can keep going. And we can actually travel to our nearest planetary destination, and that's Mars. That not only has all the elements, but it has plenty of water. You can see it there on the poles. And you can see it on glaciers about a few meters below the surface in other latitudes. And not only that, it has an atmosphere of carbon dioxide. And when you have carbon, think about hydrocarbons, sources of energy, plastics, and everything else that we can use carbon for. And these are just natural resources. Believe it or not, we also have human-made material that we have sent into Earth. This is space debris, trash that we have sent into space for almost 60 years. And that, since we have spent all the energy, why not use this material and recycle it and extract the aluminum and the chromium and the titanium and use it for a variety of applications in space. So these are some of the elements in the neighborhood of Earth. Now the question is, which space resource is more valuable? And if I were to ask each and every one of you, everybody will have an answer. You have your favorite material and your favorite mineral, your favorite element. But here the important thing is that, are we talking in the near term, medium term, or long term? Are we talking about resources that we'll bring to Earth and use them here, or use them in space? Now, if you just look at the price of metals here or minerals here on Earth, and how barely we have scratched the surface in order to get them, and how expensive it will be to actually get them from space, at this point, it doesn't make much sense to bring in from space to Earth. We have plenty of those. Unless we at some point start drilling too deep, we're spending too much power, we're causing a lot of environmental problems. And once we have an infrastructure in space, maybe we can start thinking about bringing them to Earth. But at this point, that's not the objective. The objective is to look at how we can utilize resources in space for space applications. Because think about this. The thousands of rockets that we have sent into space, all of the material has come from Earth. Every little bolt and nut and astronauts and satellites, everything has come from Earth. We depend 100% on a planet to launch things into space. And as we have learned here on Earth, that's not efficient, that's not a sustainable way to explore. It's also a very energy intensive operation due to this very strong force that we have on Earth that is called gravity. And it takes a lot of energy to dump things into space. Let me show you, for example. This is the Saturn V that took us to the moon in 19 69. But you take any rocket that you see on a launch pad, anything. You look at those rockets, and 90% of that is fuel. Fuel that is needed to launch that 10% of the rest of the rocket, and including tubes and structure, you're left, if you're lucky, to launch 2 to 4% of the rocket as payload. That means humans or satellites or things that are useful that will be in space. And that makes it also a very expensive operation. It takes about $4,000 a kilogram to send things into low Earth orbit. It takes about $35,000 a kilogram to send things to the moon. You want to go to Mars? That's about $300,000 a kilogram. I mean, that's just materials. If you want to send humans, multiply that by 10 or 50 times, because we are a very expensive species to keep us alive. So as you can see, it's extremely energy intensive, and it's very expensive to send things into Earth. You're going to say it's an exponential rising cost. Yes, it's exponential because the equation that governs rockets is exponential. If you want to go from point 1 to 2, from Earth to the moon, you're going to have to carry an exponential amount of propellant to get you there. And that makes this operation very difficult. And that is not the way that we do things on Earth. You know, on Earth, we don't carry everything with us. If I want to go from here to Washington, D.C., to join some of you over there, I don't have to bring all the fuel or all the food that I need, let alone all the chips that are very necessary to enjoy the ride. No, I mean, I go and refuel on gas stations, or I go to convenience stores along the way. Same thing will happen in space. So when the question is which space resource is more valuable, it will be those elements that will allow us to live off the land. So we don't have to bring everything from Earth that is so expensive and it costs so much energy. This is what's called in the field as in situ resource utilization. You use the resources on site. And so when you look at all these complex elements out there, interesting enough, the most important one in the near term will be the same one that we value so much, humans, everywhere we go. And that is water. Water that not only can serve humans for drinking, for growing plants, for protecting us against radiation and taking the occasional shower, but water that you can split into hydrogen and oxygen, making the most energetic propellant, rocket propellant that we know. And so think about what you can do if you have the water already on the moon, and you can utilize it for a base there or to move you around. You can split it into hydrogen and oxygen. Now you have fuel to go back and forth from a station that is going around there. And not only that, you can export it, because now you're launching it from a place with 1/6 the gravity of the moon. So that makes it less energy intensive and cheaper. So now you can start exporting it and filling out those fuel depots, those gas stations in space at different points between the Earth and the moon. And now you truly start having a refueling network in space. And that way you can no longer you have to just get rid of every rocket that you send up there. You can refuel it and continue going for years and years. You can even bring the water from asteroids and refuel these gas stations that will allow us to lower the transportation cost that is impeding it now to go further into space. That's what has holding back all the activity in space, because it's so expensive to send things into space. So this will make quite a difference. Once we have water as the fuel of space, then we can start going after just the lunar soil. Instead of bringing bricks and mortar, we can just use that for construction of habitats or any landing pads, berms, launching structures, and everything else that we want there. And then in the future, we can extract the metals for tools and spare parts, again, without having to spend $35,000 per kilogram to get it there from Earth, and then become self-sufficient at some point. Here is when we now transition from having identified the resources, which was the first thing that we needed to do of these 3 important things, to now looking at the technology to recover it. And here's where the terminology of space mining comes in. Now, mining on Earth has been very successful. We have done it for thousands of years because we have 4 important elements. We design our equipment under our normal gravity. We know how our equipment works and the traction and everything else that is needed to move it around. We know how to do it under our temperature and pressure here on Earth. We have plenty of labor, and we have plenty of power to move things around. But if you want to go to the surface of the moon or Mars or any other place, all of the things are going to be different. No longer you are in normal gravity. You are 1/6 or 1/3. The terrestrial environment changes. You have extreme temperatures and vacuum. Labor, there's not much labor there. So you're going to have to start thinking automation, robotics, power. You have to rely on solar energy or probably bring in nuclear power. So now you have to start changing your thinking completely into a new way of doing things. And so in the last 2 or 3 decades, we have been trying to adapt technology that we have developed on Earth and do that in space. So the large machines that we have here on Earth, like bucket drums and bucket ladders and backhoes, we have been adapting them on size, on volume, on power for the small operations that we're going to conduct on the moon, at least at the beginning. But at this point, we also been trying to push our thinking, our imagination outside again the planet, and start saying how is that we can design machines that can operate in very unique environments, even though they don't have to look anything like we have here on Earth. And so you have machines like this that are used for excavation that don't look very much like you will find here on Earth, but they're very unique because they can start working at 1/6 gravity. They're perfect for that. They can work on a vacuum. They don't have any lubricants that can evaporate. They can work with very abrasive soil. They can be as small as this and not only excavate, but transport the soil and then dump it. And so you can start thinking about swarms of robotic units that are going to be working together. And then if one malfunction, then you can use the other one instead of having these big, large machines like here on Earth. So you start adapting your thinking to a totally different situation. Drilling. On Earth, let's think about water, which is an important element in the near term. We don't usually drill for water. I mean, we go and extract it from somewhere else, unless you are in Antarctica that you have to go down there and provide clean water for research stations. So what about if we compare something like this and use it on the moon? And so we can drill boreholes with heaters and then heat up the ice, and that ice will start sublimating. That means it goes from solid to gas without going into liquid. And then you trap this on a tent. And then you use a cold trap here. And what you're doing is trapping that gas and turning it into ice. And then you can go back and forth to the refining plant to extract the hydrogen and the oxygen. Or you can start thinking differently to techniques that we don't use here on Earth. How about if we use a new term called thermal mining? And you start reflecting the sun rays from the top of the craters to the surface. And the moment that the ice sees light for the first time in billions of years, it's going to start sublimating, and you can start trapping in these tents. And then those vehicles can go back and forth to the plant where you do the extraction. And so we've been doing experiments like this here on Earth to get ready for this type of operations. And what you have to do is to recreate the lunar environment and then start looking at principles of how to do these thermal mining operations. So in order to recreate the vacuum of the moon, you do things in vacuum chambers. In order to recreate the temperature, you use liquid nitrogen to lower the temperature to 190 degrees Celsius below zero to actually do these experiments. You start using simulants of lunar material that we have learned from the lunar rocks. Now you can recreate them, combine it with ice, and start working with them, and then exposing them to radiation like the one they will have if you were to shine the rays of the sun on the surface. And so what you're going to see in this experiment over here is that we're going to start heating the lunar soil. You're not going to see anything coming out, but you know that ice is now sublimating, going into a gas. And the only thing you're going to see is how the surface collapses. So we turn on the lamp and you start seeing how the surface starts collapsing because the ice has been leaving a vacuum there and this thing collapses. So if we use this in order to find out what are the effects on the soil when you start evaporating all this material. Same thing on asteroids. If you go to an asteroid, these elements don't have practically any gravity. So you cannot think about having an excavator because you cannot move around there. You will have to actually anchor yourself, and that makes it very difficult. So how about using a technology called optical mining, in which you can redirect again the rays of the sun, focuses on the surface now on the asteroid, and with that now you start heating up the water. This comes out, and at the same time it breaks the rock, and we start actually drilling into this. So experiments have been done to do exactly that in the laboratory using a high intensity lamp to replicate the sun rays. You shine it on top of this sample, the water evaporates, expands, breaks the rock, and now you start drilling through the rock. This is what's called optical mining. You start drilling with light, and then the water will come out and other elements that as gases, and then you trap them into cold traps where we have tubes in which we have liquid nitrogen that is very cold, and then you condense all that material. Now you have ice that you can use as water. So this is some of the technology that we have been using. Now, what are things that are going to happen in the near future? Well, a mission left Earth this July and went to Mars, and it's going to arrive there next year. And this is going to be the first mission in which a resource has been extracted from another planetary body. It's going to take the carbon dioxide of the atmosphere, it's going to go through a fuel cell in reverse, and it's going to extract oxygen. For the first time, oxygen that you can store there, and at some point when humans arrive, they can use it for breathing or other elements or other applications. In 2023, there's going to be a spacecraft landing on the poles of the moon that is going to roam around and go to these permanently shattered regions, start drilling there and getting to the ice that is going to sublimate, and then it's going to condense. And finally, you're going to have a glass of water from a place that we thought at some point it was bone dry. So this is what is happening right now on activities from for space resources. Now let's go to the third topic. We know the resource, we know the technology, but is there any demand for this? Is there a customer? Who cares? Well, if you had asked who is the customer about 20 years ago in the United States, it was just NASA that was interested on this. But now other space agencies are jumping in. The United States Geological Survey is applying all of its knowledge on how to identify resources on Earth, and is doing it that for asteroids and for the moon and Mars. The Department of Commerce, seeing the potential of commercial activities, is now getting involved on how is that going to allow companies to operate under these conditions. And it's not just the space agency of the United States now. It is the Russian space agency, the Europeans, the Canadians, the Indians, the Japanese, the South Koreans, the Chinese, the United Arab Emirates, the Australian, even the tiny country of Luxembourg in Europe has put very significant resources into its space resources initiative. It is not just the government, it's the launch companies, the aerospace companies like United Launch Alliances that are creating spacecraft to be fueled with hydrogen and oxygen that they can extract from somewhere else. Lockheed Martin with its lander to be fueled with hydrogen and oxygen. And companies like Boeing and Northrop Grumman designing those fuel depots, those gas stations that would allow us to refuel in space. And not only the traditional aerospace companies, but the new ones like SpaceX, that is not only talking about Mars, but also had already offered to be on the moon in a couple of years with a large rocket. And Blue Origin also fueling its lunar lander with hydrogen and oxygen. And not just the aerospace companies, it's the small, the startups, the small, the medium size, the large size, or companies that used to work on something else that are getting interested in all aspects of what's called the value chain. Who's going to identify the resource, who's going to drill, who's going to excavate, extract, purify, separate, and all of the other activities that are important, power, communications, transport, to create this infrastructure to extract resources. And finally, you can say, well, this is great. You know, this is an activity in which the government, the private sector, and countries around the world are interested. It could be a great activity. But there's one important question that is left. Is this legal? Can anybody set up an operation and start extracting resources, selling it, and making a lot of money of doing this? Or are there any rules to follow in space like we have on Earth? On this, there's not much to go from. We have the Outer Space Treaty that was signed in 1967 by more than 110 countries at a time where space was considered only a matter of the United States and the Soviet Union, and many countries didn't see much value. But it gave us important articles, like Article 1, the exploration and use of space shall be the common province of all mankind. And Article 2, it prohibits claims of national sovereignty. That means no country can own a celestial body. Nobody can own the moon or an asteroid. And so later on, another treaty came around in 1979, the Moon Treaty, that this time was signed only like less than 20 countries and none of the spacefaring nations. It was not the United States, not China, not Russia, because now we started seeing that there was probably more to space than we thought before. And so when you try to extract language from these treaties in terms of what's legal and what's not, it becomes a little bit difficult because things have changed radically. So what's happening is that countries are taking now individual measures. starting with the United States. In 2015, both the House and the Senate and the President signed a document on the Commercial Space Launch Act, in which specifically allows any citizen engaged in commercial recovery from the United States, it's entitled to that resource, to possess it, to own it, to transport it, to use it, and sell it, that resource, if so wishes, as long as registered in the United States. The following year, Luxembourg followed suit as the first European nation to enable a legal framework. And just last year, the United Arab Emirates did the same. So you start seeing now countries developing their own legal procedures. And that has led to organizations like the one in the Netherlands, the Space Resources Governance Working Group, to start now gathering a variety of countries. It has about 35 members that are looking at how the whole world can get involved in all aspects of space resources so that we can all benefit from that. And so that language has now moved to the United Nations, to the Committee of Peaceful Uses of Outer Space, to start thinking about how to make this a worldwide activity. So as you can see, not only we're moving rapidly in the science and the technology, but also in all the legal and economic and environmental aspects that will require to extract resources from space, just like we have done on Earth. So if there is one thought that I want to leave you with, is that resources beyond Earth promises to give us an unlimited amount of knowledge, and not just knowledge. It will allow us to continue exploring. We can go further. We can carry larger payloads. It will allow us to stay for unlimited periods of time on the lunar surface of Mars. But not only that, it's going to develop commercial activity that can truly start incorporating space into the global economy. And that's going to depend on humans here on this planet, on Earth. So we go back to the value of Earth to make decisions of how we can learn from centuries of identifying and extracting resources from Earth, as we start looking at how to do the same thing beyond our planet, and how we can do this in space in an effective, in a responsible, and a sustainable way. And so with that, I thank you so much for having listened to this lecture, and I really look forward to the question and answer discussion sessions where we can go into discussing any aspect about resources beyond Earth. In the meantime, all the best, and ad astra to everybody. See you soon.